Let's now perform a fixed point analysis of the logistic map. So the fixed point of the logistic map is determined by the equation x star, where star now denotes a fixed point value, is equal to a x star 1 minus x star. That is, I plug in the value x star into the equation and I get the same value back. Now, because this equation is just a simple quadratic, it's easy to find the fixed points. The fixed points are x star equals 0, or x star is equal to 1 minus 1 over a. So let's analyze the stability of these fixed points in turn. So for x star equals 0. As we've seen in the previous slide in the graphical representation, what determines whether a fixed point is stable or not is the slope of the function at the fixed point. The slope of the function df by dx at x star, and when x star is equal to 0, in this case we just get equal to a. And what we saw is that if the slope, the absolute value of the slope is less than 1, then the fixed point is stable. Otherwise it's unstable. So what we infer from this is that when a is less than or equal to 1, x star equals 0 is stable. A larger than 1, x star equals 0 is unstable. So if we plot as a function of the control parameter a, the fixed point value of the equation x star, then what we have is that for a less than 1, 0 is the stable fixed point. But beyond that point, 0 is an unstable fixed point, but there's a non-zero fixed point. And so this was what we saw earlier on in the study of continuous systems. This is what's known as a transcritical bifurcation. So the very first instability in the logistic map is going from x star equals 0 to x star not equal to 0. Then let's look at the fixed point x star is equal to 1 minus 1 over a. So if we again compute the derivative df by dx at x star, this turns out to be equal to 2 minus a. So the point is that this fixed point is stable for a greater than 1 or less than or equal to 3. df by dx absolute value is less than or equal to 1. And that gives us that x star equals 1 minus 1 over a is stable. If a is larger than 3, then x star equals 1 minus 1 over a is unstable. So in this particular case, the bifurcation diagram in this range looks as follows. So here again is x star as a function of a, and now starting at some value of a greater than 1, we're merrily going along the stable fixed point. It's doing something like this. And then at 3, all of a sudden, this fixed point becomes unstable, and born out of this unstable fixed point are 2 additional fixed points. And so this is what we've seen before as the so-called pitchfork bifurcation. So let's now try and understand this behavior graphically, because this is really how we'll get a sense of what's going on. So let's now plot xn plus 1 as a function of xn. Function and the evolution of the fixed point. Here is our 45-degree line, and let's be in the range where a is larger than 1 and less than 3. So then we know that our upside down parabola crosses the 45-degree line, and so here is the value x star. And if we ask, like, how does this system evolve dynamically? If I start with the given value of x naught over here, then I go to the function to figure out where the next point is. I go over to the 45-degree line to get the next starting point, up to the function again. So I go in the staircase fashion, and ultimately we converge to a fixed point value x star. Now let's look at the same situation when a is larger than 3. So in that case, our upside down parabola is much taller. And again, there's a fixed point value here. But let's look at the evolution. Say we start at the same point as before. We start, say here, we go to the function, 45-degree line, to the function, to the 45-degree line, to the function, the 45-degree line, to the function, 45-degree line, function. And then you see that we're going around in a square. So what we see is that x star is no longer stable when a is larger than 3, and that happens when the absolute value of the slope is greater than 1. And so if I'm near the fixed point, I'm going to be driven away from it. So in fact, there's 2 values here, let's call them xa and xb, where we're basically on a 2-cycle, because once we've settled into this 2-cycle, if I'm at xa, then at the next iteration, I go to xb, and when I'm at xb, at the next iteration, I go back to xa. So I'm alternating between going from xa to xb and back again. How can we represent that or understand what's going on? And so here, what we were plotting was xn plus 1 as a function of xn. Let's instead plot, and we'll plot xn plus 2 as a function of xn. So xn plus 2, the iterate of xn plus 1. And this is nothing more than the iterate of xn of xn. And so we can define this thing to be f second iterate of x. And if we plug in the actual value of the function itself into this equation, well, f of x was a xn minus a xn 1 minus x, and then we take the function again. So if we want to write this out explicitly, this is equal to a times a xn 1 minus xn times 1 minus a xn 1 minus xn. And so for a larger than 3, for this second iterate function, the final state depends on the initial condition in a non-trivial way. There's a set of initial conditions for which one flows to the fixed point at xb, and other initial conditions where one flows to a fixed point at xa. These fixed points of the second iterate correspond to the 2 cycle of the first iterate. In addition to these 2 stable fixed points of the second iterate, there is an unstable fixed point at x star, which is the fixed point of the first iterate. It's also the fixed point of the second iterate. Let's go back and look at the second iterate function for a between 1 and 3. In this case, the function has only a single hump somewhere in the middle of the interval. So this corresponds to a stable fixed point of the second iterate function, which by definition is also a stable fixed point of the first iterate function. However, if a increases beyond 3, the function develops additional humps, and 2 more fixed points are born as a increases. So the initial stable fixed point of the 2 cycle becomes an unstable fixed point, and the 2 new additional stable fixed points of the 2 cycle is how the 2 cycle is born out of the 1 cycle.